So now we are ready to begin step 3, the analysis of our results. Now, for the analysis in this case, because we are mostly focused on what's going on in the classically allowed region, this region where x is less than 0, because this is where we are sending in our packet and we expect to find a packet returning back to us. We're going to really look at these two pieces of the solution. So we're going to focus on those and not pay that much attention actually to this exponentially decaying part, although it is also an interesting part of the story. So for the analysis, what I'd like you to notice is that if I look at my wave function here, psi, for points x less than 0 at time t, that's where I'm going to focus things. I want you to notice that it really comes as a sum of two pieces. There are two contributions. I have always these weights, and then I either have them times this complex exponential, and then times the time dependence. And added then to that is a second piece, which is again the integral of these weights, now times this factor and my negative complex exponential times once again these time-dependent parts. So I can really write then the total wave function for these locations psi less than 0 as a sum of the corresponding two contributions. There's a psi, I'll call it psi plus, all the parts that have to do with this plus I kx part, that's a function of x and t. And then there's also the other piece, which I will call psi minus, that refers to this negative complex exponential. There's a psi minus part of x and t. And we will analyze these then one at a time. So let's first focus on the psi plus. Now the psi plus of x and t, my claim was I had designed that to look exactly like my normal free space Gaussian wave packet. And if you look at just that piece, you can see that's exactly what I've got. I've got exactly the weights I had before, except now, okay, it's written as a function of k1, but that's my integration variable now instead of k. But otherwise, it's the same integral, it's the same prefactor, it's the same forward traveling wave, and it is exactly the same time dependence. So this thing really is just my normal Gaussian packet. So it looks like my usual Gaussian free space packet that we had looked at before. And I would like to repeat the analysis on this just one last time. I know this is all very familiar, but it doesn't hurt to practice as warm-up at least before we go and analyze the second piece, the psi minus piece. So for that, it's our Gaussian free space packet. We know how we would analyze this. The quickest way, of course, you could do the integral, but the quickest way to know where this packet is and what it's doing is to look at the stationary phase approximation, where we know the peak of the packet we can always locate by saying 0 is equal to the rate of change of the phase of this packet. Now, the rate of change is with respect to the summation variable. I'm summing over these k1s, right? And I want the phase to stay constant as a function of k1 when I'm at my peak amplitude so that I get the greatest contribution. So the phase is a function of k1, and I want to make sure that the derivative of that function gives me 0. But the derivative should be evaluated, of course, at the peak of the function. And I've constructed this function of k1, these weights, so that they are peaked near k0. So I want to evaluate this at the location where k1 equals k0, and that comes about because that is my peak amplitude. And then what I have to do is just pick out the phases. So as I move across my integral, these were the amplitudes, right? That's the only amplitude part. I had just figured out where the peak for that is. That then is multiplying this complex exponential, which is a phase. So I get a phase of k1x from this factor. And then finally, I've got this minus time-dependent phase from the time-dependent part. So putting that all together then, the phases that I had were just this plus I k1x. Oh, well, I is not part of the phase. The thing that multiplies the I is the phase. So I have k1x, and then minus, and the time-dependent part is just 1 h bar, remember, times k1 squared divided by twice the mass. And I then can take this derivative. The derivative partial with respect to k1 of k1x is just x. Then I have minus, and then the derivative of this with respect to k1. The 2 will cancel the 2 in the bottom. I'm left just with h bar k1 divided by the mass m, and I see I've forgotten my time t, right? The time-dependent part has this piece multiplied by t in the phase. Sorry about that. So that multiplies time t. But remember, this whole thing has to be evaluated at the peak of the amplitude, which occurs when k1 actually takes on the value k0. And this is easy to evaluate. I have x minus, so I substitute in k0 for k1. So I have h bar k0 divided by m times t. And this factor, very famously, h bar k0, that's just the incoming momentum p0, and then it's divided by m. And then finally, that is just what I thought my incoming velocity v0 should be. So this all looks very simple. Then this implies then the location of the maximum, x max, as a function of time t will just equal, well, setting this to 0, x is then just this factor times t, h bar k0 on m times t, or as we've just said, otherwise known as the velocity, the initial velocity times time t. Perfect. So that's just, normal free space packet behavior that we expect. If I sketch that out, I can try to interpret this then. I want to interpret this a little bit carefully so we can sketch what things look like. And to sketch it out, I want to consider actually kind of storyboarding this, because it turns out that inside of this solution to the Schrödinger equation, there actually is an entire story or sequence of events. So we're going to storyboard this here a little bit. And when we storyboard it, there's going to be a set of 3 different times I want to consider. There is the time t, which is much less than 0. So when t is much less than 0, my packet is centered at some very large but negative location. So if I were to sketch what's going on, it would look somewhat like this. And I'd have my Gaussian sitting over here at far to the left of x equals 0. And then there's also what happens when time is about 0, or when, say, t exactly equals 0. When t equals 0, if I plot here psi of x for t much less than 0 as a function of x, that's what I was plotting here. Here again, I'm plotting psi now of x at time t equals 0. And according to this, the peak location would be at 0. So I would have my Gaussian then packet would just be centered right here. But we want to be very careful about how we interpret this. Because notice, this piece of my solution that I'm looking at, right? I'm analyzing the psi plus, and this added to the psi minus ultimately, but this only makes sense when x is less than 0. When x actually is greater than 0, it's an entirely different function. It's this decaying exponential function that controls the behavior. But I'm just looking at this piece of the behavior right now, and this piece of the behavior only applies for x less than 0. So really what we see at locations x less than 0 at first is our entire packet, but at this point in time, all we see is sort of the first half of this packet. Over here for x greater than 0, this is some sort of mathematical no person's land, right? There's just nothing there. It's just all a mathematical fiction. So I'll just hash it out to remind ourselves of that fact. And then finally, you could have the case where t is much greater than 0. And when t is much greater than 0, right, I'd be plotting psi of x now for this time much greater than 0. When t is much greater than 0, I'm at some large positive location, so my peak is all clear of this interesting boundary region. My peak is somewhere over here. So we see our peak has been moving steadily to the right, but now an interesting thing has happened. The peak is now gone, right? It's all gone over into this imaginary regime.